One burns in minutes, the other survives centuries. The average American wood frame home lasts roughly 50 to 80 years before major structural failure. But houses built from compressed dirt, rammed earth, have stood for over 2,000 years. They can withstand 2 hours of direct flame without failing. They cut energy bills in half. And they are made from the ground beneath your feet. So if a house made of dirt outperforms nearly everything we build today, why does almost no one in the US use it? A typical American home relies on a skeleton of 2x4s and plywood, nailed together in a matter of weeks. But a rammed earth house begins with a very different process, one that looks almost primitive, yet produces walls that can outlast empires. The construction starts with formwork, usually made from heavy-duty plywood or steel panels, set up to define the shape and thickness of each wall. Into these molds goes a carefully engineered mix, about 50% sand, 20% gravel, and the remaining 30% split between silt and clay. Sometimes a small dose of cement or lime, usually 5 to 10% by weight, is added for extra strength, especially in wetter climates. This is not just any dirt. The soil must be well graded, with enough clay to bind, but not so much that it cracks as it dries. Next comes the real work. The soil mix is poured in thin layers called lifts, usually no more than 6 inches deep at a time. Each lift is compacted with hydraulic or pneumatic rams, which can deliver pressures between 2,000 and 3,000 pounds per square inch, comparable to the forces used in industrial concrete work. The ramming process fuses the grains together, squeezing out air pockets and locking the particles into a dense, stone-like mass. As each layer is packed, the wall gradually rises inside the formwork, creating a monolithic slab with no cavities or hidden voids. The result is a wall that is not just thick, often 12 to 24 inches, but solid all the way through. Standard geometry for a modern rammed earth wall is 30 to 60 centimeters wide, or about a foot to 2 feet. This is not overkill, it is essential for both structure and performance. At these dimensions, the wall acts as a massive thermal battery, storing heat during the day and releasing it slowly at night. That density also means the wall is non-combustible and resistant to pests, rot, and mold. Building codes in Australia, New Zealand, and parts of Europe set the minimum compressive strength for load-bearing rammed earth at 2 megapascals, about 300 pounds per square inch, but modern techniques routinely double or triple that figure. In the Skagit Valley project, for example, architects specified 24-inch thick earth walls with a compressive strength exceeding 2,500 pounds per square inch, sandwiching an 8-inch layer of rigid insulation for even greater energy performance. The entire assembly is built up in sections, with each form moved and reused as the walls progress. Once the forms come off, the surface reveals natural striations, each layer a record of its making. No paint, no synthetic cladding, just the color and texture of the local earth. The process is slower and more labor-intensive than a typical wood frame, but the payoff is a structure that can stand for a century or more with little more than an occasional wash. The numbers tell the story. A wall that shrugs off fire, resists decay, and keeps energy bills low, all built from the ground beneath your feet. The contrast with the throwaway logic of modern construction could not be sharper. Sections of the Great Wall of China, built with rammed earth more than 2,000 years ago, still rise from the Loess Plains. Archaeologists have dated the Jiangku and Mutianyu segments to between 210 BCE and 150 CE. Their cores comprised of compacted local soil mixed with lime, layered by hand and tamped to a dense, stone-like hardness. These walls stand not because they were forgotten, but because they were maintained. Accrue every 30 years, imperial records say, reprofiling the outer face, patching the capstones, and preserving the structure against centuries of rain and wind. The original earth, when tested in modern labs, still shows compressive strengths of 5 to 7 megapascals on par with newly built rammed earth today. The same story plays out across continents. In Morocco, the fortified granaries of Et Ben Haddou and the Dades Valley have stood since the 12th century, their three-layered earth walls surviving over 600 years in a semi-arid climate. In Yemen's capital Sana'a, earthen towers, built in the 13th century, still house families, their flexible cores absorbing earthquakes, their surfaces renewed by community replastering every 20 years. Roman engineers, too, trusted compacted earth. At Pompey's Villa of the Mysteries, loam footings, laid before 70 AD, remain intact beneath stone columns, their density and self-healing crust confirmed by modern conservation teams. What links these structures is not nostalgia, but performance. Rammed earth, when properly detailed and maintained, endures for centuries. The numbers are not marketing spin, they are archaeological fact. Core segments of the Great Wall have survived more than 2,000 years. Moroccan and Yemeni earth buildings routinely reach 400 to 900 years. Roman compacted earth footings protected by stone and drainage have lasted 1,900 years and counting. The story continues in the laboratory. In a standard ASTME 119 fire test, a 30-centimeter thick, cement-stabilized rammed earth wall withstood over 2 hours of direct flame without structural failure. The surface cracked, the core held, no flashover, no collapse, just a wall that refused to burn. For comparison, a wood frame wall under the same test lost integrity in less than 15 minutes. The fire rating achieved by these earth assemblies matches or exceeds that of reinforced concrete and far surpasses the combustibility of conventional framing. The fire performance is striking. This combination, multi-century longevity and proven fire resistance, stands in sharp contrast to the typical American home, where a 50-year lifespan is considered normal and fire remains an ever-present threat. The evidence is buried in plain sight, from ancient fortresses to modern lab reports. Earth, when compacted and cared for, does not rot, does not burn, and does not surrender to time. The science behind this performance, thermal mass, density, and mineral chemistry, will come into focus next. But the record is already clear. The limitation isn't the material, it is the system built around it. A wall made from earth does something that wood and drywall simply cannot. It slows down the movement of heat, turning the entire building envelope into a kind of thermal battery. The science behind this is both simple and profound. Dense, compacted soil absorbs heat during the day, holding it deep within the wall, and then releases it slowly, sometimes hours later, as temperatures outside begin to fall. This lag, measured in real-world homes and labs, typically ranges from 8 to 12 hours. In practice, that means the mid-afternoon heat does not reach the inside until well after sunset, and overnight, chills are kept at bay until morning. The effect is visible on a daily temperature graph. Outdoor highs might swing by 20 degrees Celsius between noon and midnight, but inside a rammed earth house, the peak arrives late, and the overall swing shrinks to just 4 to 7 degrees. In hot, dry regions, field studies have logged interior temperatures staying 5 to 7 degrees cooler than the outside during the hottest part of the day. In rare cases where walls are exceptionally thick and the climate is extreme, the interior has stayed up to 10 or even 15 degrees cooler. But most occupied homes report a more modest, yet still impressive moderation. This is not just a laboratory phenomenon. Homeowners in New Mexico, Spain, and the Pacific Northwest have tracked their own comfort, sometimes with nothing more than a digital thermometer and a notepad. One Skagit Valley owner noted that even without running the heat, winter indoor temperatures rarely dropped more than 3 degrees Fahrenheit overnight. In the summer, the walls soaked up the afternoon sun, keeping the living room comfortable until well after dark. These are not isolated anecdotes. Academic monitoring of occupied rammed earth homes consistently finds a thermal lag of 8 to 12 hours, with daytime peaks delayed and nighttime lows cushioned. The result is a steady, stable environment that feels almost disconnected from the weather outside. Passive design sketches often show south-facing windows paired with thick earth walls, allowing the sun's energy to be banked during the day and released after sunset. This is not about insulation in the conventional sense. Rammed earth's R value is modest compared to fiberglass or foam, but about thermal mass, and the physics of time. The walls act as a buffer, smoothing out temperature spikes and reducing the need for mechanical heating and cooling. The numbers add up to real savings. Field-monitored homes report 30 to 50% lower energy use for heating and cooling compared to similar wood frame houses. In some cases, utility bills have dropped by nearly half, and owners describe a kind of comfort that does not depend on constant adjustment of the thermostat. The wall does not care if the power goes out or if the air conditioner fails. It simply responds to the sun and the seasons as it has for centuries. The physics is clear. A dense, well-built earth wall can turn the daily cycle of heat and cold into a gentle, delayed rhythm. The comfort is not a marketing claim, it is a measurable, lived reality. Yet despite the evidence, this approach remains rare, sidelined by a building industry that favors speed, standardization, and short-term economics over long-term performance. The conversation around costs tends to start and end with the construction budget, but that narrow focus misses the bigger picture. On paper, building a rammed earth house often means a higher upfront bill, anywhere from 12 to 20% more than a standard wood frame home, according to recent life cycle cost studies from China, Australia, and North America. The main reason is labor. Compaction, formwork, and careful soil preparation demand more time on site and a crew trained in techniques that are not part of the mainstream builder's playbook. Material costs, by contrast, are surprisingly modest. The earth itself is usually free or nearly so, sourced from the building site or nearby, with only a small outlay for cement or lime stabilizer, typically just 5 to 10% of the wall's dry weight. But the initial sticker shock fades when the full lifespan comes into view. A typical wood frame house in the US is designed for a service life of 50 to 80 years and often needs major repairs, replacing siding, patching rot, battling termites within the first 2 decades. By contrast, properly built rammed earth structures routinely reach 100 to 500 years, with the oldest segments of the Great Wall and the Moroccan Keisauer still standing after centuries. The difference is not just in the walls themselves, but in what those walls do not require. There is no paint to peel, no drywall to replace, no studs to warp or mold. Maintenance schedules from historic and modern case studies converge on a simple pattern: an exterior wash every year or two, and a fresh coat of lime or earth plaster every 15 to 30 years, depending on climate. In Yemen and Morocco, community replastering is a cultural event, not a crisis. In the Pacific Northwest, homeowners report no repainting or termite issues after a decade, just a quick power wash to keep the natural color bright. The numbers behind these claims are not theoretical. A Chinese comparative study tracked annual repair costs at just 80 cents per square meter for rammed earth versus $1.50 per square meter for brick concrete, mainly due to the latter's vulnerability to moisture and cracking. In Spain, insurance premiums for earth homes are 5% lower than for conventional builds, reflecting their fire and seismic resilience. Financing, too, is shifting in places like Kenya, where banks offer interest rate discounts for low-carbon, high-durability projects, rammed earth among them. The real kicker is the payback timeline. When lower energy bills and minimal upkeep are factored in, most case studies find that the upfront cost premium is recovered in 6 to 8 years. After that, the savings compound. Over a 30-year mortgage, the total outlay for a rammed earth house can be 20 to 30% less than for a wood frame or brick concrete home, even before factoring in the longer service life. The silent witness to all of this is the spreadsheet, columns tracking construction outlay, maintenance intervals, and energy bills over decades. What it shows is simple. The wall that costs more to build costs less to own. The wall that takes longer to raise stands longer, asks less, and gives more. The argument that rammed earth is too expensive or too high maintenance does not survive a look at the numbers. The real barriers do not lie in the material or the math. They lie in the systems that decide what gets built and what gets left in the ground. Across the world, the numbers are hard to ignore. In China's Hunan province, a life cycle assessment compared a modern rammed earth home to a conventional brick concrete house of the same size. The results Embodied carbon for the rammed earth build came in at just 241 kilograms of CO2 per square meter, more than 40% lower than the 417 kilograms measured for the brick concrete structure. The difference comes down to ingredients. Where conventional walls rely on cement and fired clay brick, materials with high energy and high emissions production, rammed earth uses mostly local soil, with only a small fraction of cement or lime, often less than 10% by weight. The soil is usually sourced within a few kilometers of the site, slashing transportation emissions to almost zero. The same pattern holds in Spain. A comparative study in Valencia found that rammed earth walls reduced embodied carbon by 42% compared to fired clay brick, while in Iran, the gap was nearly as wide, as a life cycle assessment showed a 38% drop in total embodied energy for rammed earth over the local brick standard. Even when a stabilizer is added, the carbon footprint of a rammed earth wall remains 28% to 45% lower than that of a typical masonry wall. The numbers are not outliers. A 2024 review in the journal Sustainability aggregated dozens of regional studies and found that, across climates and building types, rammed earth construction cuts embodied carbon by 40 to 45% on average. For a world trying to meet net zero targets, these reductions are not a footnote. The wall itself becomes a carbon solution, not a liability. On paper, the case seems overwhelming, yet despite the evidence, rammed earth remains a rarity in modern housing. The reasons have little to do with the material and everything to do with the system that decides what gets built. Building with earth in the United States means running into obstacles that have nothing to do with soil or structure. The first is the permit process. Most building codes mention wood, steel, and concrete, but rammed earth is left out. When plans land on a municipal desk, clerks flag them for extra scrutiny. Requests for engineering reports, peer-reviewed data, or full-scale mock-ups are routine. In California, alternative wall systems face review periods 30 to 45 days longer than standard wood frame proposals. The absence of code language acts as an invisible barrier, stalling projects before they begin. If a permit makes it through, the next challenge is financing. Mortgage underwriters rely on comparable sales, but rammed earth homes are so rare that lenders see only risk. Some demand 30% down, far above the usual 20%. Others decline outright, citing a lack of actuarial data. Insurance companies, too, treat earthen homes as outliers, even with proven fire resistance. Insurers often charge premiums 10 to 15% higher, especially in wildfire zones. The missing claims history outweighs the material's actual performance. Construction itself moves at a different pace. Rammed earth crews build about half a square meter of wall per hour, while wood framers cover 2.5. Developers, focused on speed, resist schedules that run 30% longer. The supply chain for standard materials is streamlined, and earth building remains niche and costly. These hurdles are not technical failures. They are the result of code gaps, lender caution, and a system that rewards speed and sameness, not innovation. Today, a home built from rammed earth can stand for centuries, shrug off flames, cut energy use by up to 50%, and leave a fraction of the carbon footprint. Yet wood frame homes, costlier over time, shorter-lived, more combustible, remain the industry standard. The limitation is not the science or the soil, it is the system built around it. What would it take to change what we call normal?